Another phenomena associated with sound waves is beats. Whenever you have two sound sources with frequencies that are near to each other, its frequencies are different, but they are near to each other, then you have this kind of interference pattern. And in this interference pattern, at one point, you will have constructive interference. At another point, you will have out of phase destructive interference. Then at a third point, constructive interference, and so on and so forth. So we have this pattern. This pattern is oscillating between loudness and lack of loudness, loudness, lack of loudness, etc. The frequency of this pattern, which we call it beats, the frequency of the beats is determined from this formula. It is equal to the difference between the two frequencies. F2 minus F1, the absolute value here, determines the frequency of the beats. You are tuning a guitar by comparing the sound of the string with that of a standard tuning fork. You notice a beat frequency of 5 Hz when both sounds are present. You tighten the guitar string and the beat frequency rises to 8 Hz. To tune the string exactly to the tuning fork, you should. So here, as we tighten more, the beat frequency gets higher. We want this to go to 0 if we can, in order to say that this is the tuning is done. Okay, so in this case, the right answer, you need to loosen the string a little bit so that you reduce the beat frequency. Another point when we talk about sound is the quality of sound. Quality of sound. If you consider the sound for a tuning fork, this is the kind of wave, sound wave generated, and the frequency will be just the fundamental harmonic, one frequency. And if you consider a flute, same frequency, but as produced by a flute, not by a tuning fork, you will have a complex pattern like this. If you analyze this pattern, you will note for the relative intensities, this is the first harmonic, this is the second harmonic, the third harmonic, the fourth harmonic, the fifth, the sixth, the seventh, etc. You will see that the second harmonic has the highest intensity. You will note also that fourth harmonic and first harmonic have the same intensity level. So this complex structure determines the quality of sound generated by a flute. Another example, the clarinet here at the same frequency. Again, you have this pattern for the intensities of various harmonics that interfere together and determines the quality of sound generated by the clarinet. The human ear is a good example to study as we study sound. Here you have the ear canal. At the end of the ear canal, you have the eardrum here. So the compressions and refractions of air, which are variations in the pressure for the air in the atmosphere, will act on the drum, and the drum will oscillate back and forth depending on these compressions and refractions waves. As it does so, the oscillation is transferred by these three segments, the hammer, the anvil, and the stirrup, and then carried by the oval window to the nerve, the audio nerve, and from there to the brain. This is how we hear sounds. Any defect in this system will lead to a defect in our ability to hear sounds. This is a representation for the sound intensity as measured in decibels. for various levels taken at 1000 hertz. Usually the comparison we do it between these intensities at 1000 hertz. So this shows the frequency response curve for an average human ear. Our ears will sense sounds, but our ability to distinguish sound depends also on the frequency of the sound. The use of the term sound waves in air is meant the position of air, the velocity of air, the pressure variations in air, the displacement of air, the flow of energy through air. We know that compressions and refractions, changes in the pressure of air. So yes, this is the answer. Sound waves meant the pressure variations in the air. Which of the following wavelength is common to a 10 centimeter tube open at both ends and a 15 centimeter tube open at one end? So for the one opens at two ends, the length is related to half lambda. The one open at one end is the length is related to 1/4 lambda. So this would be the right answer. This can be multiples or related to 10 and 15. We are done with this chapter. In this chapter, we learned about the property of sound waves. We learned about the audible range, 20 hertz to 20 kilohertz. We learned about speed of sound in a medium, determined from elastic property over inertial property. For fluids and gases, it's the bulk modulus divided by the density. For solid rods, Young modulus divided by the density. We learned how speed of sound changes with temperature, and calculate that from this equation. Remember to substitute T in Kelvin in this equation. We learned about the intensity, which is the power per unit area, and how to use the decibel scale, 10 logarithm the intensity I compared to the threshold of hearing. We learned about spherical and plane waves, and the intensity there is the average power divided by the area of the sphere, 4 pi r squared. We learned about Doppler effect, how the observed frequency differs from the source frequency because of the motion of the source and the observer, or one of them. Then the interference of sound waves can lead to extra loudness or less loud, depend on the path difference between the two sources. We have constructive interference when the path difference is integer multiple of lambda, and we have destructive interference when it is n plus 1/2 lambda. Then we talked about standing waves in strings and in pipes. We learned that the frequency for any harmonic is integer multiple of the fundamental harmonic. We learned about beats, which is the difference between the two frequencies.